Yeah, so we're very happy to have our last speaker of the whole conference. So Ben Schweinhart, who is gonna give us the third part of his mini course. And just for some of you that might not know, he's right now assistant professor at George Mason University. And he's going to tell us about percolation and topology. And yeah, thank you very much, Ben, for being here.
All right, thank you again, and thanks for the introduction and the opportunity to speak. Before I get started, I want to say if you have had the time to pay attention to all of my talks, thank you very much. And if you're interested in this, I am interested in working with PhD students in the areas of stochastic topology, as I've been telling you about, and topological and geometric data analysis. I have some projects in mind in the area of percolation and topology, which is what I'm talking about now. I also have some other projects in stochastic topology, project with Erica on different random growth models and lots of other interesting stuff. But if you're interested in working with me, I encourage you to apply for the math PhD program at George Mason University. If you want more information, you can email me about it. There's also a virtual open house next month. So either email me or you can send an email here to get more information on registering for it. So please let me know if you're interested. Okay, so on to the main talk. Okay, so last time and the time before, we were talking about events in bond percolation in ZD, where we were interested in the emergence of a giant component in bond percolation on the integer lattice. And last time, we also talked about head percolation in the three-dimensional integer lattice, where the event we were interested in was the event where a rectangle was bounded by a surface of plaquettes. And here I would like to tell you about analogous events to the first one, to the emergence of the giant component in a compact setting where we have the torus. So you see here that this path here, it goes from the left and it meets up at the opposite point on the right. So here we're on the torus. This is the flat torus, and we want to view it if we go this way and we come back around on the same side on that, like this. And if we go up and we come back to the same side here. So here we have the periodicity in the square, which gives us a flat two-dimensional torus. And here we view this finite analog of the infinite component that we study in bond percolation is a path that wraps all the way around the torus. So you see here that we start here and we come back to the same point on the other side. And here is an event, a rotated event, where we start at the bottom and we go to the top. And this is in fact the same point here because we've identified opposite sides. And this can be generalized to provide a higher dimensional notion of homological percolation, as was done by Bobrowski and Skraba. And so today I will explain this notion of homological percolation to you and discuss a theorem that my collaborators and I have proven about homological percolation, showing a sharp phase transition. So the objects of interest in homological percolation are so-called giant cycles. And these, roughly speaking, if you haven't seen algebraic topology, are going to be possibly singular submanifolds of the d-dimensional torus that wrap all the way around the torus. So here is an example of a one-dimensional giant cycle. These two are one-dimensional giant cycles. So one manifolds, loops, which wrap all the way around the torus from one side to the other. So here is an example of a two-dimensional giant cycle in the three torus. So again, here we have periodicity with left and right sides, front and back, and top and bottom. So here is a sheet, a giant two cycle that wraps from one side of the torus to the other. And we'll have a more formal definition soon. Yep.
I have a question here. By possibly singular, what will be singular or not singular?
So this is an interesting question in classical topology. So if you know about so the question is really getting a little ahead of myself. If you have a singular homology class, right? What can that be represented by? And there's a theorem of René Thom, I believe, that says that it can be represented by a map of a manifold. So the surject, the image of a manifold under a continuous map. So that's what I mean here. And then, of course, there's the question of what singularities can emerge. And that's beyond the scope of this discussion, but feel free to ask me about it later and we can discuss it. But I just want people to have this picture in mind that we have, in the 2 case, we have a surface spanning the torus, but it may not be a surface. You may get some self-crossings, right? So you may have some singularities, but the picture I want you to have in mind is a surface spanning the torus. Yeah, and we want to show something about a phase transition about when these giant surfaces appear. Homological percolation was introduced, higher dimensional homological percolation, that is, was introduced by Bobrowski and Skraba in this a paper appearing in Physical Review E in 2020, where they conduct a number of interesting computational experiments about homological percolation with several different percolation models, including several of the ones that we discussed at the beginning of the 2nd lecture. So I think they looked at the Gaussian free field. They looked at, they didn't look at Plaquette percolation. They looked at Gaussian free field. They looked at continuum percolation and site percolation on both the square and triangular lattices and generalizations to higher dimensions. And they noticed a number of interesting phenomena, such as an apparent relationship between the expected Euler characteristic curve, which is something you can write down exactly, and the observed percolation thresholds. They didn't line up exactly, but they seem to be close to each other. So this is a cool paper, and I encourage you to look into it if you're interested in that. And they all, Bobrowski and Skraba also had a 2nd paper on homological percolation from last year, where they looked at continuum percolation, where you put down random disks in a torus. And they looked at the emergence of these giant cycles. And they were able to prove a sharp phase transition for one-dimensional giant cycles. And some other results about giant cycles in other dimensions. They were able to show they exist, but not able to show the existence of a sharp phase transition. Okay, so they studied a lot of models. Here I'm mainly going to be talking about one model, which is a continuation of the models we were talking about last time, which were plaquette percolation. So here we start with the TND to be the torus obtained by identifying opposite faces of the D cube, 0 n to the D. So we have a cube of linear width n. And then we identify opposite faces, and that gives us a flat D-dimensional torus. And then this has a natural cubical complex structure, given exactly the same way as the cubical complex structure we saw in plaquette percolation ZD last time, which is we have this cube. It has these integer lattice points, and you can use that to break it down into big N to the D unit cubes. But as you can kind of see here we just have some of the plaquettes from the cubes. And then we define I-dimensional plaquette percolation with probability P to be the random cubical complex obtained where we start with the I-1 skeleton. That means we add in all of, say, if we're doing 2-dimensional plaquette percolation, this means we start with all the vertices and all the edges. And then we add in the I plaquettes independently with probability P. In the case of the picture here, we're adding each of these 2-dimensional squares with probability P. And so this gives us a random cubical complex. And that is the structure we are going to study. And the main theorem we proved. Were you going to say something?
Yeah, I have a question there as well. So you're taking basically like a linear Mechoulam model where you are just deciding to cut having the I-1 dimensional skeleton. And then...
Yeah, we start with the I-1 skeleton, and then we add the I things with probability P. So in that sense, it is analogous, yes.
Okay, yeah, thanks.
What's different is that we're doing it based on this cubical complex rather than a different one. Yeah.
Yeah, so it's
that will give us the generalization of bond percolation. Yeah.
Yeah.
Okay. Thanks for the question. Yeah, I probably should slow down a little. So please ask questions. I think I did introduce this last time, so I'll try to go a little slower from here on out. So what my collaborators Paul Duncan and Matthew Kale wanted to do is we wanted to find a finite volume analog of the Harris-Keston theorem. So recall that the Harris-Keston theorem told us that PC equals 1/2 is the critical threshold for the emergence of the giant component in the 2-dimensional integer lattice. And recall that in the proof of that, as I talked about in the last 2 lectures, we use the self-duality of the integer lattice at criticality at PC equals 1/2. And if you think about this plaquette percolation, if you have half-dimensional plaquette percolation with probability 1/2, then you get the same self-duality phenomenon. So we wanted to prove that we got a phase transition at PC equals 1/2 for this higher dimensional model. And that's exactly what we did. We proved that if we have half-dimensional plaquette percolation on an even dimensional torus, then the characteristic of the field where we're taking homology does not equal 2. I'll talk about this later. I realize that this hasn't been explained yet. This has something to do with the symmetry of the homology group, as we'll see soon. Then the probability that we have no giant cycles, so we have no spanning manifolds of half-dimensional spanning manifolds, goes to 0 as if P is less than 1/2. And the probability that we get in some sense, a basis of giant cycles goes to 1 if P is greater than 1/2, as the size of our torus goes to infinity. So we show a sharp phase transition for the emergence of giant cycles. And in my talk today, I would like for you to understand this result, both what is homological percolation and to give you an overview of how we would prove this result. Okay. So first, let me begin with a topological review. Now, you've probably seen some other definitions of homology in other talks in this workshop. So I hope this isn't too repetitive, but I just wanted to, I thought for completeness, I should give some definitions of homology in the case we're looking at of a cubical complex. So homology gives the space of giant cycles a vector space structure. So to formalize this, we need to go over briefly a few topological definitions. So given a cubical complex X, we can define the chain group Ci of X to be the vector space of formal linear combinations of I-dimensional faces of X with coefficients in some field K. We'll have a picture in just a second. So here, for example, so here's our chain complex X. One example of a one chain would be E1 plus E2 plus E3 plus E4. Another example, an example of a 2 chain would just be sigma. Okay. And what's cool and what allows us to define homology groups is the fact that we can define a very natural and geometric linear transformation between the chain group of dimension I and the chain group of dimension I minus 1. And the way we do that is by defining the boundary map. So here, I guess here we only have 1, 2 cell and 4 edges named. So I can just tell you what the boundary map here is for that. We say that the boundary of a face sigma is the signed sum of the I minus 1 faces contained in it. So here we have sigma has 4 faces, E1, E2, E3, E4. So we say that the boundary of sigma is in order E1 plus E2 plus E3 plus E4. Okay. And then we can extend that to the whole vector space of I-dimensional chains to give a linear map. So here we define the I boundary map. We take the boundary of sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. And you can work it out that if you just take the sums, and it's important that you take the signs here. This is why we have the signs, is that the boundary of sigma 1 will be this edge plus this edge plus this edge plus this edge. And when we add the boundary of sigma 2 here, this is going to be the opposite edge, so it cancels out. So you'll see that the boundary map, the boundary of the sum of these, four 2 cells, right, is just the boundary of the big square that's their union, like this. Okay. So this is admittedly very fast, but I want to get on to some deeper stuff. So I hope you have absorbed this from some other talks. So you'll see something about what's going on. So now to define homology, what we do is we let Zi of X be the kernel of the boundary map. So this is the vector space of cycles. So just looking at the figures here, so we have chains. So this is here's a few examples of one chains. So the one chains are just going to be sums of, I guess we don't have some coefficients here, but we normally have coefficients. So I guess here all the coefficients are 1, say. So here are some examples of chains. So there's no, no restriction on which collection of edges we choose, right? And then so a cycle is going to be a chain that doesn't have boundary. So here are some examples of chains that don't have boundary. So we take the boundary of this, we get nothing. And we're on the torus here. So when we take the boundary of this, we also get nothing, because this is the same point as here. Okay. And then we also define the vector space of boundaries to be the image of the boundary map in dimension 1 above. So you can see here that we have shaded, we have these two cycles here are boundaries, because this one in orange down here is the boundary of the 2 chain that we get by taking the 3 squares in the interior. Okay, and importantly, this one going across here, this is not a boundary. Think about why it's not. Okay. And then we can define the I-dimensional homology vector space as the quotient of cycles mod boundaries. For example, up here we have 2 chains, 2 one chains here, which is the one given by the dashed blue line and the one given by the thicker orange path going like this. So you can see that these both connect at opposite ends of the torus. These are both one cycles, loops, but they represent the same element of the homology group, because their difference is a boundary, as is shown here. The boundary of this, I guess, teal region here, or turquoise region, is the difference between the blue striped region and the orange region. Okay, so homology allows us to look at cycles mod boundaries. And so this is really cool if you haven't seen this before and you think about it. Like, if you look in these tori, right, if you look at this cubical complex Tn to the d, right, you're going to have the number of cycles and the number of boundaries is going to the dimensions of those are going to go to infinity as your torus grows, right? But when you take the quotient, you get a finite dimensional vector space, which doesn't depend on your choice of n. So that's really cool, and so it's a nice topological invariant for these. Okay. So what's going to be very important in my talk is the example of torus. So I'm going to see a few examples of homology groups of the torus. But in general, a basis for the I-dimensional homology of the D-dimensional torus is given by the I-dimensional planes in the coordinate directions, of which there are d choose I of them. So here is an example of a basis of giant cycles taken from a simulation of plaquette percolation. Two-dimensional, a basis for the two-dimensional homology of the 3 torus is given by these. And we'll see more about what these are in just a second. But okay. Here is an example about the I-dimensional homology, the one-dimensional homology of the 2 torus. This claims it's given by the green cycle and the orange cycle, right? So then you could come to me and say, what about the purple cycle? If you pay attention closely here, you'll see that this is in fact a cycle, because if you go here and you go here, you come to this point. You go here, you go here, you go to this point. So it's a loop around the torus. And you can see that this one is actually the sum of the green and the orange. We do need to have a direction on these, which I'm not included just for to make the figure look nicer. But if you orient them the right way, you'll see that the difference between the purple one cycle and the sum of the orange and the green one cycles is this gray shaded region. So in fact, the difference between them is a boundary. So okay, a little bit more about these bases of cycles on the torus. So the standard basis for the one-dimensional homology of the 2 torus is represented by the lines in the coordinate directions. So here recall that the torus TD, right, is the product of S1 D times. Is topologically the equivalent of D circles, where here the circles are given by the by exactly this, the lines in the coordinate directions. So here, the standard basis are these lines in the coordinate directions, which are just S1 cross 1/2. Here I don't have that particular one drawn, but this is homologous to it, and 1/2 cross S1. So like that. Okay, so these are circles. The basis for H1 and T2 is given by, you can view it as cycles that are represented by circles. Okay. And then if we go to the two-dimensional homology of the 3 torus, the standard basis is given by the coordinate planes, which are here going to be S1 cross S1 cross 1/2, S1 cross 1/2 cross S1, and 1/2 cross S1 cross S1, for example. Okay. So what are these topologically, right? So we had our a basis for the 1 homology is represented by circles. And so the 2 homology is going to be surfaces with singularity spanning the torus. So which surfaces are these? Well, these are just 2 tori, right? We have S1 cross S1. This is a 2 torus. So here we have a basis for the 2 homology of the 3 torus, where each of these, they look like a plane in my figure. But remember, we're identifying opposite sides, right? So we have this square with opposite sides identified. So that's, again, a flat torus. So hopefully that gives you at least some idea of what these giant cycles can be. They're these cycles that are represented by these surfaces spanning the torus, and they have a nice vector space structure. Okay. Okay. So a giant cycle then is going to be a cycle. So we have P is plaquette percolation on the torus. So this is going to give us a random subset of the torus, right? So this is going to have some homology, right? But some of it is not going to be non-trivial when we map it to the torus. So here is an example of one-dimensional bond percolation of the torus. And we can include it into the torus. And some of the cycles here are going to be boundaries in the full torus, and some of them are not. So the giant cycle is a cycle that is not a boundary. So only this one bold blue one is a giant cycle because it's not a boundary in T2. So more formally, the function that includes, so there's a continuous function from our plaquette system to the d-dimensional torus given by just inclusion. And it turns out that this induces a linear map on the homology from the vector space, the I-dimensional homology of the plaquette percolation P to the I-dimensional homology of the D torus. So we get a linear function here. And then we say that a cycle in the I homology of the plaquette system is a giant cycle if it's not 0 when we map it to the homology of the torus. So the image of phi star is a vector space because, as I've said, this phi star is a linear map induced by this here. So we can ask, the events of interest are going to be, well, the random variable of interest is the rank of phi star, which is in some sense the number of linearly independent giant cycles in our plaquette system. And in particular, the main theorem we want to show is that there's a phase transition between having no giant cycles, the rank of phi star, the dimension of the image of phi star being 0, and getting a basis of giant cycles. That is, the image of phi star is the homology group of the torus. Okay.
Ben?
Yes.
I'm a bit confused with this slide because I thought we had the complete skeleton there, and here I guess the reason why these two, the one with only 1 square and the one with 4 square, the reason they are yeah, I don't know why you're including those 2 cells and not the other ones, because
it's because on the left, right? On the left we have no 2 cells, right? On the left is one-dimensional plaquette percolation. So we start with all of the vertices and then we add the edges independently with probability P, right? And here we're mapping it into the whole torus. So in the torus you have everything, right? You have all the 2 cells, all the edges. I probably should have, in this figure, I probably should have had dashed lines for all the edges to show that they're there. And then it would have been more clear, right? So we map this thing where we don't have any 2 cells into a thing where we have lots of 2 cells. And we ask which cycles remain non-trivial.
Yeah, okay. So you don't have the whole one skeleton. You do have.
On the right side, we do.
On the right side, yeah.
On the right side, I should have included all of them, right?
Yeah, okay, thanks.
On the right side, we have all of them, and we have all the 2 cells. So that's going to kill some of our cycles, in particular this one and this one. Okay.
Yeah, thanks.
Okay. Okay. So so now we have our events of interest are that we have no giant cycles and that we have a basis of giant cycles. So we want to now use duality theorems from algebraic topology to try to show some self-duality occurs for half-dimensional plaquette percolation. And the way we do that is first by defining a dual plaquette system. So we talked about this briefly last time for this special case of two-dimensional plaquette percolation in Z3. But in general, if we have d-dimensional plaquette percolation, either in ZD or in this torus we've constructed, we can define the dual plaquette system by shifting our lattice by 1/2 in each coordinate direction and considering the d minus I dimensional plaquettes. And like we had for two-dimensional plaquette percolation in Z3, we have this duality relationship where an I-dimensional plaquette of the original system intersects exactly one d minus I dimensional plaquette of the dual system in its center. So we can couple I-dimensional plaquette percolation with probability P with d minus I dimensional plaquette percolation with probability 1 minus P, as in bond percolation in Z2, where we couple one-dimensional bond percolation with probability P with dual bond percolation with probability 1 minus P. And so it's not just of interest, we have a coupling. We can define a coupling, right? But this is a coupling where P and P bullet have a very nice geometric relationship to each other. And that geometric relationship is formalized in saying that if we take the complement of P in the torus, this deformation retracts to the dual system. This means that we can collapse the complement. So if you haven't seen what a deformation retract is before, we can collapse the complement. The complement of P to the dual system. And this implies that they have, among other things, this implies that they have the same homology groups. So in this picture here, I'm proud of making this picture. It took me a while to make this. You can see here that we have our system P is the blue bonds, right? And our dual system is orange. And what we can do here is if we remove the blue system from the torus, you can collapse everything else in the torus to the orange system along the arrows. And you actually do that in 2 steps. First, going along the gray arrows, right? So you can deform the, you can collapse the complement of the blue system to the one skeleton of the dual system along the gray arrows. And then you can collapse the remaining edges that are intersected by a blue edge, rather, to the vertices along the black arrows. So this shows that there is a very strong geometric relationship between our plaquette system P and our dual plaquette system P bullet. Here, I actually want to delete my notes. Okay. And so there's a common topological principle, which is if you decompose a compact manifold into 2 complementary subsets that are nice enough in a certain way. So this is not true in general. Your 2 subsets have to be nice in a certain way. Then they should have related homology groups. So you can actually, so you recall from my first lecture, we were talking about a statement about rectangle crossings in bond percolation, right? Where you have a horizontal crossing in our bond percolation, if and only if you do not have a vertical crossing. So this can actually be restated in terms of a homological duality principle about the relationship between the, I guess here you'd get a system of hexagons and squares and a dual system of hexagons and squares. And you can prove it the same way. But another example of this topological principle it tells us a relationship between the giant cycles of P and the giant cycles of P bullet. And this is the statement here, that if we consider so here this is, let me add in some, because some of you, this may be new notation to a lot of you, let me actually attach English words to some of these. So this is the number of linearly independent giant cycles. In P. And this is I-dimensional. I-dimensional. And this is the number of, so we could just copy and paste that in P bullet, which is D minus I dimensional. So this tells us that if we take the number of linearly independent giant cycles in P plus the number of linearly independent giant cycles in the dual plaquette system, then that adds up to the total number of giant cycles in the torus. Number of giant cycles in the torus. Okay, the maximum possible number of linearly independent giant cycles. In particular, we have two special cases of interest, which is A is the event that P has at least one giant cycle. So this is the case that the rank of phi star is greater than 1. And S is the event that we have a basis of giant cycles, that is the rank of phi star equals D. And then as a corollary to the duality lemma, we get that here at least one of the events A and A bullet occur, where A bullet is the corresponding event for the dual system. Because, well, the ranks of one of them has to be greater than 0 if they add up to D, which is greater than 0. And also, we get no giant cycles in our plaquette system if and only if we have a basis of giant cycles in the dual system and vice versa. So this tells us, so we have this nice coupling between our plaquette percolations, and we have a strong relationship between the events of interest, that we get no giant cycles and that we get a basis of giant cycles, is they are dual to each other. Okay. So here, this is a nice result. So I wanted to say just a couple words about the proof of it in case you've seen some more algebraic topology. The proof of it goes very similarly to the proof of Alexander duality, if you've seen that, which says that if you're in a sphere, there's a relationship between the homology of a subset of a sphere and the homology of its complement. To prove that, you set up a commutative diagram like so, and you do some diagram chasing. So I won't go through this. I'm not assuming background in this, but if you're interested, it's in our paper. And also the papers of Bobrowski and Skraba, they prove similar results for other percolation systems on a torus. So they have proofs there as well. Okay. Are there any questions? Okay. So now that I have my topological tools and definitions, we're going to switch to doing more probability. And I want to give you a sketch now of our main theorem, which is to remind you that if we have half-dimensional plaquette percolation on the torus, and so with homology, we had a coefficient field. This is where we took, when we did our formal sums of plaquettes, formal sums of, plaquettes, we had some coefficients in some fields. So here we're going to require that the characteristic of our field doesn't equal 2 for reasons I will elucidate later. So in that case, we can show that the probability that we get no giant cycles goes to 0 if P is less than 1/2, and the probability we have a basis of giant cycles goes to 1 if P is greater than 1/2. So to prove this, we use 3 different ingredients, all of which can be interpreted as a form of symmetry. We have our duality lemma from a couple slides ago. So in the case of half-dimensional plaquette percolation, this is a symmetry. We have at PC equals 1/2, we have that that our half-dimensional plaquette percolation is self-dual. It's dual to half-dimensional plaquette percolation, or you have to mention all plaquette percolation in the dual at PC equals 1/2. So there's one symmetry. The second symmetry I will tell you about is a symmetry of the homology of the torus, which I'll give you a definition of an irreducible representation on the next slide. But this basically says that if the characteristic of our field isn't 2, then our homology is an irreducible representation of the point symmetry group of the torus. And then our third local symmetry is going to be the local symmetry on the level of the plaquettes, that we have a transitive group action on them by the total symmetry group of the torus, where we allow translations as well. So we can map any plaquette to any other plaquette. And that symmetry allows us to apply this theorem of 3 Gutting-Kalai, which I'll tell you about later as well. So we have 3 different symmetries. Here, let me tell you about the second symmetry now. So basically, in simple terms, the symmetry probability we want to have, symmetry property we want the homology of the torus to have, is that for any non-zero element of our homology group, we want to be able to spin up an entire basis out of just that element of the homology, and then looking at its image under the symmetries of our symmetry group. So that's this statement here, that the homology of the torus will be generated by G sigma, where G is in our symmetry group. And this is equivalent to something called HI of TD being an irreducible representation of the symmetry group. So if you've seen this before, maybe forgotten the details, let me just say what the definition is. So an irreducible representation of a group G is a vector space V, which is acted on by G, so that the only G invariant subspaces are 0 and V. So what we're saying here, up here, is we're looking at a line, right, in our vector space, the line generated by sigma. And this is telling us here that the line generated by sigma, if we take all of the images of that under the symmetries of our torus, then that will give us a basis. Well, that would give us a spanning set, rather. It might not be linearly independent. It will give us a basis for the homology of the torus. Okay. So here, I'm going to show you some more specific examples of this, this property, and we'll have a proof that the one-dimensional homology of the 2 torus has this property here in a couple slides. But here, let me tell you what the spinning lemma is. So the spinning lemma says that if the homology of the torus is an irreducible representation of the point symmetry group of the torus, so we have this homology is nicely symmetric, and we look at the probability that we have a basis of giant cycles, that tells us that we can bound it from below in terms of the probability that we have at least one giant cycle. And this fundamentally has to do with the fact that if this spinning lemma is true, or if this if we have an irreducible representation, then if we have any giant cycle, we can use the symmetries to show, hey, under the symmetries we get all giant cycles. So that's very roughly how you go about proving this. And in fact, that will give you a proof if you have F as a finite field. You can just go through it like that. Otherwise, you need to do some thinking about using the fact that it's an irreducible representation, in addition to this statement I had about the lines. Anyway, so if you haven't seen irreducible representations, this may look a little complicated. So here I want to go to some specific examples. So what is the symmetry group of this flat torus? We can write this torus as the product S1 times S1 times S1 times S1. Okay, the product of D copies of the circle. Then the point symmetry group. So this is the symmetries that fix a point. So we also have translations, which I'll mention later. But here we're looking at ones that fix the point. This is the hyperoctahedral group, which is also the symmetry group of the D cube. And this is generated by permutations of the S1 factors. So we can move our S1 factors around. And we can also reverse the orientation of a single S1 factor. So I call those reflections. And then a fact is that if the characteristic of F does not equal 2, then these homology groups are irreducible representations of the symmetry group. Okay, let's see some examples, as I promised. So here, as before, the standard basis for the one homology of the 2 torus is represented by the lines in the coordinate directions. So here are 2 examples. Here's a basis of the homology of the 1 torus. So we can permute the S1 factors in our product S1 cross S1. So here is, there's, I guess, one non-trivial permutation in this case, where we switch the x direction and the y direction. And that switches the two basis elements of the torus like this. Yep. And we also have the reflection. So the reflection is going to reverse the orientation of one of our coordinate directions. So here we reflect it, and you see we go from going around the torus in this direction to going around the torus in this direction. So that's the action of the symmetry group of the two torus on the one-dimensional homology. And we can see just from that that H1 of T2F is an irreducible representation of W2 in the case where characteristic of F doesn't equal 2. So we'll see why we need that on this slide, actually. So to show that this is an irreducible representation, we let sigma 1, sigma 2 be the basis of the homology seen on the previous slide. So S1 cross 1/2 and 1/2 cross S1. And we take a look at a generic element of the homology, A sigma 1 plus B sigma 2. And here I should say that this is a non-zero element of the homology. So as I said, when I first started talking about this, we want to spin this up into a basis for the torus. And that will show that this is an irreducible representation. So since gamma is not 0, then either A doesn't equal 0 or B doesn't equal 0. And since the directions are symmetric, we can assume without loss of generality that A doesn't equal 0. So now what we can do is we can take rho is the reflection across the x-axis. So this is going to send sigma 2 to negative sigma 2. Okay, as we saw in the previous slide. So if we do that, then if we take 1 over A times gamma plus P gamma, you'll see that our sigma 2 term will cancel out. Yep. We add it, and then its reflection across the x-axis, we get it to cancel out. And since we divide by A, we get 2 sigma 1. Okay. So we've shown we can spin up one of the basis elements from any non-zero element of the homology. And then given one of the basis elements, we can just permute it to get the other basis element. Okay, so we swap the x and y axes, then S1 cross 1/2, or the homology class represented by S1 cross 1/2 becomes the homology class represented by 1/2 cross S1. So this tells us from the single non-zero element, we can spin up a basis for the homology. So I have this question down here. Where did we use that the characteristic of F doesn't equal 2? Erica, did you notice?
We divided by 2.
Yeah, so we divided by 2 right here, right? So this is the problem, right? If characteristic of F equals 2, actually it's not an irreducible representation. You can show that. This isn't a proof it's not an irreducible representation. This proof doesn't work, but you can show it's not irreducible. And the problem is that if you look at the homology class 1, 1, right? If you take A equals 1 and B equals 1, right? Then that line is invariant, is an invariant subspace. So you're not irreducible. Okay.
But is it expected that it's a question of the technique of the proof, but not actually something that will not happen when you have a characteristic of the field?
So I would hope that our main theorem holds in general.
Yeah.
For the method of the proof, we need the characteristic to not equal 2 because we need this symmetry. If you can think of a way to prove it for characteristic 2, that would be cool. Or if you can think of a way to show that it's not true, right? You could imagine there being like somehow, if you look at what surfaces in the 4 torus, right? Then your homology here is going to distinguish which ones are orientable and which ones are not, right? And in fact, there should be some relationship to that. And if you take your coefficients in Z2, you don't have an irreducible representation. There should be some relationship there. So maybe there's something else weird going on with non-orientable surfaces spanning the torus before orientable surfaces or something like that.
Yeah.
But I would be very surprised.
Okay.
I would be very surprised. Yeah, that's a good question. Okay. And let me just point out that for our higher dimensional homology of the torus, we can have a similar, we can also look at the action of the symmetry group on S1 cross 1/2 and so on. So you'll see that, again, the permutations of the coordinates permute them. And if we reflect, then we have the orientation is reversed, which is multiplying by -1 in homology. And in fact, the fact that this is an irreducible representation of the symmetry group can be proven directly from this here. We have a different example of a different type of percolation where we have to rely on some theorem to show some theorem for the representation theory literature to show that we have an irreducible representation in all the cases we claim. But here it's straightforward and elementary. Yeah, just by looking at these actions. Anyway, okay. So the spinning lemma tells us that if we have the event that we have our number of giant cycles is greater than 0, then we can spin up a basis from a single giant cycle. And using some nice probability theory arguments, we can show that that implies the probability that we get all giant cycles is bounded below from 0 if the probability of having one giant cycle is bounded below from 0. And then the next step after that is to show that if so that's this hypothesis here. We get this from the spinning lemma. If this is greater than 0, the spinning lemma says that if this is greater than 0, then PPS is greater than S is greater than 0 for some little s. Okay, that's what the spinning lemma tells us. And so our next step is to show that this, in fact, applies that the probability that getting all giant cycles goes to 1 if we take Q greater than P. And this follows from the local symmetry I mentioned, which is that we have if we look at, I don't know why I lost the line here, but anyway, so if we look at the full symmetry group of the torus, we also have translations. And then the full symmetry group of the torus acts transitively on our two plaquettes, for example. If we're looking at two-dimensional plaquette percolation, we can take one two plaquette to any other two plaquette. And the fact that we have this symmetry on the plaquettes tells us that we can apply the theorem of Fried-Gutting-Colley, which says is very powerful, very strong theorem saying the existence of phase transitions in general. It says let B be an increasing event that is invariant under a transitive group action on X. So here our increasing event is that we have a basis of giant cycles, that if this is increasing because if we add in more plaquettes, we only have plaquettes in dimension I, so we can't kill I cycles. So there's our increasing event. It is invariant under a group action on X, having a basis of giant cycles. If we rotate our torus, it's not going to change that we have a basis of giant cycles. The Fried-Gutting-Colley tells us that if this event is bounded away from 0, then we get, okay, this looks a little complicated, but this tells us that if the size of X is large enough and we increase our probability Q, right? If Q is greater than P, I probably should have that somewhere on the slide. Yes, Q is greater than or equal to P plus some amount, then the probability we get a basis of giant cycles is greater than 1 minus epsilon. So this is a general threshold result for increasing events that are invariant under transitive group action. So this theorem here will imply our proposition here about having a basis of giant cycles once we have the spinning lemma, which I just told you about. So those are our 3 elements of symmetry. And with them, we can prove our main theorem, that PC is 1/2 is the critical probability for half-dimensional plaquette percolation. So consider I-dimensional plaquette percolation on the 2I-dimensional torus. So self-duality implies that the probability that we have at least one giant cycle at 1/2 in our plaquette system equals the probability we have at least one giant cycle in the dual system, because they have the same distribution. Then we can apply our first symmetry, the duality lemma, which says that the number of giant cycles in A plus the number of giant cycles in a bullet equals D, big T, the rank of the homology of the torus. And in particular, at least one of the events A and A bullet have to occur, which tells us that the probability of A at 1/2 plus the probability of A bullet at 1/2 is greater than or equal to 1. And that tells us that the probability of having at least one giant cycle is greater than or equal to 1/2 in half-dimensional percolation. Okay, let me pause for a second so you can process that. Okay, so we have to have at least one giant cycle in either A or A bullet, because the number of giant cycles in each has to add up to the total number of giant cycles. And since they have the same distribution, that tells us that our probability that we have at least one has to be greater than 1/2. Okay. And then we can apply the preceding proposition to say that if P is greater than 1/2, the probability of getting all giant cycles then goes to 1. Okay, so we get that sharp phase transition. And now we want to consider what happens below the threshold. Well, on the other hand, the event that we get no giant cycles, right? This is the same as the event that we get a basis of giant cycles in the dual system, right? So just applying this same result here to the dual system tells us that the probability we get at least one giant cycle goes to 0 as n goes to infinity in our original Plaquette system. So we have multiple applications of the duality limit. Okay, how am I doing on time? Okay, I'm almost at an hour, so I can tell you a little bit more. Any questions about this? Okay, hopefully I didn't go too fast. I guess, if you haven't seen homology before, this is probably too fast, but hoping you have in the other talks here. Okay, so that's our main theorem. And so we also have some further results. So you can ask, what happens when we don't have half-dimensional percolation? Do we get a sharp threshold there? So what we're able to show is something slightly weaker than that. We can show that there is a sharp threshold function, that some function of n, so that if we go slightly above it, the probability we get all giant cycles goes to 1. And if we're slightly below it, the probability we get no giant cycles goes to 1. The probability we get at least one giant cycle goes to 0. So the issue here is that we have this family of tori we get from identifying opposite sides of a cube of linear width n, right? So they don't fit naturally one into the other, right? So we can't directly compare what goes on in one torus for one value of n to torus with the value n plus 1. So we aren't able to show that there is a single real number that we can use as our threshold function, as we did here in the case d/2. However, we can show that for one-dimensional Plaquette percolation, this is bond percolation on the torus, and d-1 Plaquette percolation, it's dual, that we get, that we can take our threshold function to be a constant. And that will correspond to the critical probability on ZD, for bond percolation on ZD. Okay, so we have this partial result, and we have, so let me say that the proof of this is exactly the same as the proof of our main theorem. It just breaks down because we have this lambda event. I guess it takes a little bit more work, but the proof has the same 3 key elements. And we can show some, even when we can't show the existence of a single PC, we can show that there is some partial duality results. In particular, if we look at, so we take our threshold function, we can look at the lim infin and the lim sup of our threshold function. So away from half-dimensional percolation, it could be bouncing down in some up and down in some window, right? But we can show pretty simply that the lim inf and the lim sup are bounded away from 0 and 1. And we can show the partial duality property that PC plus QC equals 1. In some sense, this says that having a sharp threshold function is equivalent to duality between PC of ID and PC of D minus ID. And then we can also show that the PC of IDs are monotonic in the dimension. If we reduce the dimension, our critical threshold is higher. That makes sense. Or if we increase the dimension of the homology, our threshold is higher, which also makes sense. Okay. So that's it for what I have to say about Plaquette percolation on the torus. So in my remaining 15 minutes, I think I'll take maybe 5 minutes to tell you about another result, and then I will stop for questions. So you may recall from actually at the beginning of my talk last time, I said you can also prove that PC equals 1/2 for site percolation on the triangular lattice. So this is where you can view it as this so-called face percolation here, where we take these hexagons and we end them independently with probability P. And if we do that in the plane, our threshold for getting an infinite component is PC equals 1/2. So we would hope that we can make a higher dimensional generalization of that in the torus as well, and we can. And that is, we're looking now at site percolation on a lattice called the A star D lattice. I don't have time to define that for you today. But in dimension 2, it is the triangular lattice, and its Voronoi cells are hexagons like this. And if we go into higher dimensions, the Voronoi cells of the A star D lattice are D-dimensional permutahedra. So where a permutahedra is an example of a polyhedron with some nice symmetry properties that relates to the symmetric group on D+1 letters, actually. So here are an example of 3-dimensional permutahedra. So Bobrowski and Skraba showed that the same duality lemma about homology holds when the plaquettes and dual plaquettes are replaced by occupied and unoccupied permutahedra. So we can take this setting now, and we can apply our same tools, our same 3 symmetry tools, and we can prove here's the special case of our main result. If we take site percolation on the permutahedral lattice on the 4 torus, we showed this result for the D torus, but I like the 4 torus result for a reason I'll say in a minute. And now a key difference with plaquette percolation is in plaquette percolation, only I-dimensional homology is of interest, right? Only the, we start with the I-1 skeleton, and we don't add any cells of dimension greater than that. Whereas here we're adding in these permutahedra, and we don't start with any skeleton, right? So all the homology groups are interesting. All the homology groups change. So now we have 3 events, which are the events that we have a I-dimensional cycle for here in the 4 torus, 1-dimensional giant cycles, 2-dimensional giant cycles, and 3-dimensional giant cycles. And we can show, using our same results, that if the characteristic of F does not divide D+1, this is exactly when SD+1, the symmetry, yes, the HI TD is an irreducible representation of the symmetric group on D+1 letters. If you know that, I just wanted to say this. So that's where the spinning lemma comes in. Then we can show we get 3 different sharp phase transitions. And the reason I like the case equals 4 is these are all 4 known values. We get a phase transition for 1-dimensional giant cycles at the critical probability for bond percolation on the A4 star lattice. We get giant surfaces, roughly speaking, appearing at 1/2, where we have self-duality. And then we get giant 3 cycles appearing at dual to the threshold for A4 star. Okay, so that's pretty cool. Yeah, so that's our main result for this site percolation on the permutahedral lattice. Okay, so there's a number of future directions I'm interested in studying in this area. So the big question, of course, is we've proven a finite dimensional analog, or rather a higher dimensional finite volume analog of the Harris-Keston theorem. But we would ideally like to prove a infinite volume, a version in the full integer lattice. So that is interesting going forward. Another question we can ask is what happens at criticality? So I mentioned briefly last time that there's these beautiful results about critical site percolation on the triangular lattice. And then we get observed in computational experiments universality between different models. Is that true here? I would like to explore that in computational experiments. And also, can we, can we get some sharper results? Can we remove some of the hypotheses on the characteristic of the field? Can we go to a torus that's a rectangular torus rather than a square torus? And also, can we develop a quantitative understanding of what happens in our subcritical and supercritical regimes? Okay. So here are the references for my talk, and thank you for bearing with me for all three of these talks, and thank you for your attention.
Thank you so much, Ben. Yeah. So I don't know if someone has questions. If not, I have a couple, but Tony?
No.
Okay, then then I'm gonna take advantage of my position of chairing.
Mm-hmm.
So Ben, what if so below criticality or even above, as you know, we could study the finite components, right?
Yes.
And then in plaquette percolation, even if we only think of the two-dimensional plaquette percolation, plaquette model on 3D,
Yes.
we will have VII and VII.
Yes.
And what happened in the model of two-dimensional, we have been observing that at PC we're seeing like the maximum number of holes into D. But what do you think is going to happen to the finite, in this case, that we have two variables, right? VII and VII in this plaquette model. Which one do you think is going to go to the to which thresholds?
Okay, that's an interesting question. And I think actually the answer is probably going to be a threshold, which I haven't mentioned here, but related to your question from the last talk, right? So you asked in the last talk, why don't we look at the, I guess you asked two questions, right? Why don't we look at the threshold for the emergence of the giant component, right? So that's one thing, or the emergence of a giant surface. So those are others. And I believe we can show that those are all distinct. So I'm guessing that that in the finite components, the VII and VII will be maximized at the threshold for the emergence of the infinite component in plaquette percolation.
In each one of the respective.
That's my guess. I could be wrong. Yeah. That's my guess. Let's do some computational experiments.
Let's do some computations. The other question that I had was if one could easily understand, for example, these tube systems that I asked you last time, right? Like how far apart are they? And I'm kind of thinking on what is going on in the hyperbolic case, because I thought that was not happening in the 3D, but after you mentioned it, I think we could have a lot of space empty, even if there is an infinite component in the usual way.
I think we should talk about this more. I don't have a good answer right now, but we should talk about it later.
Okay.
Yeah.
Great. Yeah. I don't know if someone else have questions.
So on your first question, right? So you can ask, you can use some duality, right? You can, instead of looking at the components, right? You can look at the dual to what you have been looking at, which is these finite, I guess, in bond percolation, in finite bond percolation clusters, right? And the dual to that is you can take the bounding surface, which makes it a finite run, right? So then you get these random surfaces by duality. Does that make sense?
But could be not connected. Like we could have chunks, and then the question is which chunk to observe. I guess this is the problem of actually trying to study the finite components by doing experiments in the.
Well, you have a natural choice, right? Which is if you're doing two percolation in 3 dimensions, right? Two bond percolation in 3 dimensions, right? You could take the surface which separates your cluster at the origin from the outside, right? So that gets you a random plaquette surface, right? A random finite plaquette surface. Not of a given size, but corresponding to a given size of cluster.
Yeah.
And then you can use some duality results to say what its statistics are going to be.
Yeah, okay. That is doable. Yeah.
And then again, the thing is that you don't have a fixed number of size, but you can see some analogy between where you'd want the threshold to happen, right? Like that should say that you have two different models. They're not exactly the models you want, but it will say that where the maximum is, right? And the maximum in this modified model occurs at the dual to the bond percolation threshold, which isn't going to be the threshold for the emergence of giant surfaces in plaquettes. So maybe I was wrong with my first guess.
No, but it's an interesting problem, and I have never run experiments like that, and I guess I don't even foresee how variance be, even if we fix p, how much the number of tiles that have the 0, 0, 0, 0, it's gonna vary. Okay. Yeah. Okay, we should talk about it more.
Yeah, we should talk about it.
Great. So if there are not more questions, we thank Ben again for this wonderful mini course that he gave us. Yeah, thank you very much, Ben. And thank you to everyone who has been with us, Tony. We, on behalf of both, and also to all the speakers, to everyone who gave a mini course. Yeah, do you want to say something else, Tony?
No, I just want to repeat that. I really enjoyed everyone's talks. I'm really happy with all the mini courses went, and really the quality of the talks I thought was excellent. So really without exception. So yeah, thank you everyone for doing so much really great work, and thanks to all the people in the audience that participated and who joined us. Even though you didn't join us in Gather Town, we're happy to have you on Zoom here, which is the more important part. But yeah.